This video will discuss the photochemistry of transition metal complexes. In other words, how is the chemistry or the reactivity of a transition metal complex different when the excited state of the complex is involved? So first of all, let's just look at an example that is very well studied, and that's the example of transition metal carbon monoxide or carbonyl compounds. By way of review, we need to know that, remember that carbon monoxide is a gas, and also that it is a strong field ligand. And it's a strong field ligand because it is a sigma donor, like all other ligands, but it can also act as a pi accepting ligand. So again, here's the example of CO acting as a sigma donor, and then down in the bottom, we can see that carbon monoxide can actually accept electron density from the metal to form a pi bond between the metal and the carbon of the CO ligand. And that's going to be important in the photochemistry. So let's assume that we've got a D1 carbon monoxide complex, and we shine light on the complex, and an electron is promoted from the T2G to the EG star set. So in this case then, we're taking an electron from a relatively bonding, or at least slightly bonding orbital in the T2G because of the pi accepting nature of the ligand, and giving it to an anti-bonding orbital. So we're taking bonding density and creating anti-bonding density. This lowers the bond order between the metal and the ligand, and that's going to tend to cause the carbon monoxide ligand to dissociate. Typically then, if we want the CO to dissociate, if we bubble nitrogen gas through the solution, that's going to tend to sweep the CO away from the complex and up and out of the solution, which will prevent it from recombining with the original metal. And if we happen to have multiple carbon monoxides in the complex, the first one is lost relatively easily, the second one with a bit more difficulty, the third with even more difficulty, and so on. And the reason for that is that, again, carbon monoxide is a pi accepting ligand. So when we have that partial double bond character between the metal and the C, and as we start to lose carbon monoxides, the back bonding actually increases, so the COs are held more tightly. In addition to that D to D type transition, it's also possible for a complex to have a charge transfer reaction. And in the charge transfer, we're not going D to D, but we're going from a metal orbital to a ligand orbital, or vice versa. So to see what that looks like, let's look at the complete MO diagram for a transition metal complex. So we can see that right here is the usual simplified part of the MO diagram that we're often concerned about with transition metal complexes, the d orbital splitting diagram. But if we've got an octahedral complex, we have bonding orbitals down below, and then anti-bonding orbitals above. And if we have a ligand like bipyridine, there are pi accepting orbitals from the bipyridine ligand that aren't really directly involved in the complex formation, but are part of the overall complex. So in addition to the typical D to D transition that we could see, it's also possible to take a T2G electron and transfer it to an anti-bonding orbital in the ligand. Now this typically doesn't cause ligand dissociation because it isn't a metal ligand anti-bonding orbital, but it does put an electron into the pi star system, in this case of the BIPI ligand. So that has the effect of oxidizing the metal and reducing the ligand, because we're taking an electron from the metal T2G set and putting it in the ligand anti-bonding. So this changes the redox properties of the complex. So in order to have an MLCT, metal to ligand charge transfer, we need obviously a set of metal d electrons and then a ligand with low-lying pi star orbitals. These transitions don't violate the Laporte rule. It's not G to G, so therefore epsilon tends to be big. It's also possible to have a ligand to metal charge transfer. And this is something we would typically look for if we've got a ligand that has two pairs of electrons or more on it. One is the pair that is the sigma donor pair to the complex. The second pair is a pi donor pair of ligands. So that produces an extra energy level filled with electrons right here in the diagram. These are the pi electrons on L. Those electrons can be transported or transferred in an excited state from the ligand then to the empty metal orbitals. So again, ligand to metal charge transfer, which is also a Laporte allowed transition, so epsilon is big. So in summary, in the excited state, antibonding orbitals tend to be occupied, so ligands tend to dissociate. CO dissociates efficiently because it's a gas and can be bubbled out of solution, but pretty much any ligand can be made to dissociate if we occupy the T2G or the EG star set of orbitals. And then if we use a metal to ligand charge transfer or ligand to metal charge transfer, the redox properties of the metal and ligands change. So in other words, if we access the excited state or unexcited state of a complex, different chemistry happens than we see thermally or in the ground state reactions for the molecule.